In this talk, I want to talk about communication lower bounds for perfect maliciously secure MPC. And this is joint work with my advisor, Ivan Damgaard. So the setting that we're considering in this talk is that of perfect maliciously secure MPC, where we have a group of n mutually distrusting parties who wish to compute some public function on their private inputs. And the network proceeds in a synchronous manner, and we denote by T the number of malicious corruptions, where for now we're going to assume that we have a maximal threshold of n equals 3T plus 1. So these corrupted parties may deviate in an arbitrary manner from the protocol being described. And we consider an unbounded adversary and perfect security, which means the adversary should learn nothing about the private inputs of the parties that couldn't be gathered from the public output of the function. So first of all, what do we mean by communication complexity? The first observation is that we can always compute this function f by simply sending all the inputs to some trusted third party and letting her do the computation and send back the results to the parties. And this is going to have a communication complexity which is linear in the size of the inputs. So the question that we pose is, compared to this naive setting, what overhead, if any, is required to compute the function f with perfect security? And in order to avoid trivial cases where the communication is large, simply because the output of the function is large, we only consider functions which have a small output compared to the input. And a different and probably much harder question, which we do not explicitly answer, is whether or not there is a lower bound that grows with the size of the function being computed. So our results are as follows. For any number of players and sufficiently large input, there is a function f such that any secure two-phase MPC protocol that evaluates the function must communicate at least omega ns bits. And I want to emphasize that the result only applies, technically speaking, to two-phase protocols, where the protocol is naturally split into an input phase, where the parties commit to their inputs, and then a computation phase, where the computation is actually performed. And this is a very natural restriction to make, since pretty much all maliciously secure MPC protocols exactly have this two-phase structure, since we don't want the adversary to be able to choose their input as function of the honest party's inputs. And I want to emphasize that, the reason is that we need this explicit point in the protocol execution where all the inputs have been committed to. And this captures reactive functionalities which natively have this property that they maintain a state which they update, for instance, in verifiable secret sharing. And even more is true. So we can compute this function f from the lower bound using a linear sized circuit, which means that for any number of players, there is some sufficiently large circuit with G gates such that any secure MPC protocol must communicate omega ng bits. So in other words, any generic MPC compiler must communicate O of n bits per gate in the worst case. And in the submaximal threshold setting, where we have n equals 3t plus s, the lower bound is weakened by exactly a factor of s. So some related work. The work most related to this is by Damgaard, Larsen, and Nielsen, who consider the exact same questions that we do, however, for passive security. And they also show an overhead of O of n communication per gate for the maximal threshold setting. And for n equals 2t plus s, the bound is also O of n over s. And note that while any actively secure protocol immediately yields a passively secure protocol, we can't immediately use this bound to show a bound in the active security setting, because in order to be able to apply this lower bound, we need to set s equal to t plus 1, in which case the lower bound becomes trivial because t is linear in the number of parties. There's also work that shows a bound on the number of messages which need to be exchanged, but this is only interesting for small inputs. And we want a lower bound that grows with the size of the inputs to the functions. There's also a bound that grows with the circuit size, but it only works for so-called gate-by-gate protocols, and we wish to pose as few restrictions on the protocol being run as possible. So the setup is as follows. We have n parties denoted P1 up to Pn, which are connected by pairwise secure channels. And we denote by f the function that we want to compute, where each party Pi has an I-bit input vector xi that consists of I bits. And like I mentioned, we consider so-called two-phase protocols, which implement the standard functionality for secure function evaluation with perfect UC security. And I should note that we can actually make do with much simpler assumptions than those in UC security, but we choose UC security mainly for simplicity of exposition. On the technical side, what we do is that we bound the entropy of the transcripts in the input phase and show that the entropy has to exceed a certain quantity, which means that the parties need to communicate more than this quantity. And we start with the four-party case, and then we lift this to the general n-party case. So in the four-party case, we have four parties denoted P1 up to P4, and we have exactly one corruption. And we consider the following function that we denote IP I, 4. So it takes an input from each party, x1 up to x4. Then it concatenates this into a large vector and chooses a random index among the 4i different indices and outputs the index as well as the corresponding bit of the large vector. And the reason we choose this specific function is twofold. First of all, as we'll show later, this function can be computed using a linear sized circuit. And second of all, it has the following crucial property, that whenever any of these four parties changes their input by even a single bit, the output distribution also changes. And since we consider this the setting of perfect security, this will allow us to derive a contradiction that we'll need later. So the main theorem of the four-party case is that in any protocol that securely evaluates IP I, 4, the party P4 must communicate at least omega I bits. In order to prove this, we'll denote by Ti the transcript of the player Pi in the input phase, and we want to show that the entropy of the transcript of player 4 exceeds that of the entropy of the input of player 1. And this means that on random inputs for player 1, player 4 must communicate at least as much as player 1 contributed to in their input. So it suffices to show the following two things. First of all, that the entropy of the input of player 1, given the transcript of player 2, equals that of the entropy of the input of player 1. And secondly, that the entropy of x1, given both T2 and T4, equals 0. And the intuition for this is that while T2 leaks nothing about x1, and T2 and T4 together leak everything about x1, then all the information that was contained within x1 must have also been contained within the transcript for player 4. And we can show this more formally using the chain rule for Shannon entropy. And as I mentioned, if T2 leaks nothing about x1, but T2 and T4 leak everything about x1, then T4 must contain as much information as x1. So now I want to show these two claims. For the first claim, we want to show that the entropy of x1 given T2 equals that of x1. So this is actually not too hard to see, because we need to be able to perfectly simulate a corrupt player P2 that plays honestly in the input phase without knowing the output. And this is where the crucial property that the protocol is two-phase comes into play, because when the simulation needs to produce the output of the input phase, it doesn't yet know the output of the function. So this is the first claim. For the second claim, we need a lemma, first of all. So suppose we have a protocol that evaluates a function that has this crucial property that I mentioned before, namely that the output distribution changes whenever any of the inputs do, and assume that a corrupt player is honest and inputs some input x1, then the simulator for that party must send x1 on behalf of that party. And again, this is not too hard to see, because if the simulator sends anything different, then the distribution must also be different, which is a contradiction with perfect security. And now we are ready to show the second claim. So we want to show that the input for player 1 is in fact completely determined by the transcripts of player P2 and P4. So suppose, for the sake of contradiction, that x1 is in fact not completely determined by the transcripts of T2 and T4, then there must be some input distinct from x1, say x1 prime, that produces the same view for P2 and P4. And now we're going to consider two different scenarios and attempt to derive a contradiction. So in the first scenario, we have the four parties P1 up to P4, which have their respective inputs x1 up to x4. And suppose that player P3 is corrupt, but plays honestly in the input phase. And in the computation phase, she's going to pretend as if player P1 had the different input x1 prime instead. And we're going to call this scenario A. In the other scenario, we're going to have a corrupt player P1 that has an input x1 prime and plays honestly in the input phase. However, after the computation phase, she's going to pretend as if she had input x1. And we're going to call this scenario B. So note that in these two different scenarios, the computation phase must be exactly the same. So the output distribution must also be exactly the same by perfect security. However, by the previous lemma, the simulation must use x1 in scenario A, and it must use x1 prime in scenario B. By construction, the output distributions must be distinct, which is a contradiction since we just showed that the output distributions must be the same. And this means that our assumption that x1 was not completely determined by T2 and T4 was false, and therefore x1 is in fact completely determined by T2 and T4, which shows the previous lemma that P4 must communicate at least as much as the entropy contained in the input for player 1. So now we want to generalize this to the n-party case. And we want to show that any n-party protocol that computes IP I, n must have a total communication of omega nti. And we're going to do a reduction from IP ti, 4 to IP I, n. And the first observation is that any party here can act as the player P4. And we can arbitrarily group the remaining 3T parties into 3 groups of size T. And this is going to give us a protocol for IP ti, 4. And note that if we corrupt any of these 4 parties, it's going to result in at most T corruptions in the n-party protocol. And since the n-party protocol is secured by assumption, this is going to give us a protocol for IP ti, 4. And hence the previous lemma that we just showed must apply here. So this means that the party P4 must communicate at least omega ti bits. And now what we're going to do is that we're going to apply this procedure to all of the n parties and add up the communications. And this is going to overcount each bit by exactly a factor of 2. Since we have point-to-point channels, each bit is going to be counted exactly once at the sender and exactly once at the receiver. However, since we're considering the asymptotic complexity, this is of no concern. So this shows that any n-party protocol that computes this function must have a total communication of omega nti. The next thing we want to show is that this function can in fact be computed by a linear sized circuit. And this is not too hard to see. So suppose the input is an exact power of 2, and denote by boldface R a random tape filled with uniformly at random bits, which is going to be of size k. And now we're going to do a simple induction in k. So if we have k equals 0, then we have a single input bit, And to choose uniformly at random among a single input bit is to simply output that single input bit. And if we have k greater than 0, then we're going to split the input into two equal sized halves, x0 and x1. And by induction, we're going to have circuits C0 and C1, which choose uniformly at random amongst the bits in each half. And we're going to let Y0 and Y1 denote their output gates. And now we're simply going to compute the union of the two circuits and add an additional output. So the output here is essentially just going to use the kth bit of the random tape to choose uniformly at random between these two outputs from the inductive step. And this is going to, since the kth bit of the random tape is also uniformly random, this is going to choose uniformly at random between all the bits in the input. And so this is uniform, and the size is going to be twice that of the previous size plus some constant stuff, which shows the desired complexity. And this allows us to show the main theorem, which is that there is a family of Boolean circuits of size G, such that any maximal threshold n-party protocol that perfectly securely evaluates the circuit must use communication omega ng. And this follows directly from the previous two lemmas that we just showed, since the number of corruptions is linear in the number of players. And by corollary, any generic n-party MPC compiler must have a worst case communication complexity, which is O of n per gate. So some simple extensions that we can do to use on this result. So first of all, we can consider the case of submaximal threshold, where we have n equals 3t plus s for some integer greater than 0. So we can do a similar reduction as we did in lemma 2. However, now we're going to have O of t over s ways to partition the honest players into sets of size s, instead of t ways to partition them into sets of size 1. And this is going to exactly weaken the lower bound by a factor of s. And in the case of arithmetic circuits, where we have a field whose elements require k bits to describe, we're going to do exactly the same line of reasoning, except now the entropy of the input for player 1 is going to increase by a factor of exactly k. And this is going to strengthen the lower bound by a factor of exactly k. So now I want to briefly consider some upper bounds and compare them to the lower bounds that we showed here. So in the case of arithmetic circuits of sufficient size, a recent protocol by Goyal, Liu, and Sung gave a protocol over arithmetic circuits of sufficient size that has a communication complexity which is O of ngk plus n cubed k. And our results show that their protocol is optimal with respect to their circuit size. And in the case of submaximal threshold, for 3t plus s, we can use packed secret sharing to exactly save this factor O of s in communication. And our results show that packed secret sharing is the best generic optimization that one could hope for in the submaximal threshold setting. However, this still leaves open the question of Boolean circuits, because known techniques incur an overhead of O of log n for Boolean circuits, since we need an extension field large enough to embed all the n distinct evaluation points. So in the paper, we show an optimal protocol for computing the exact function that we use for the lower bound based on so-called multiplication-friendly embeddings, where we can take a vector of field elements and embed into an extension field such that products in the extension field correspond to coordinate-wise products in the base field. And this allows us to amortize the computation by essentially evaluating multiple similar circuits in parallel, and allows us to shave off exactly this log n factor for this specific family of circuits. And what we do is essentially exploit the fact that the circuit has this nice recursive structure that allows us to amortize the computation. And it's unlikely that there is a generic protocol for Boolean circuits that matches our lower bound. So to summarize, If we let n be equal to 3t plus s, then any generic MPC compiler in a field whose elements require k bits to describe must use a communication which is O of nk over s per gate in the worst case. And the lower bound is tight when the arithmetic field is of sufficient size. Future work to prove whether or not this O of log n overhead is indeed inherent for Boolean circuits in general. And as I mentioned in the beginning, we only considered linear sized circuits in this lower bound, and it would be interesting to figure out whether or not there is a lower bound that in general grows with the size of the circuit being computed. But this is probably a much more difficult question. Thank you for listening to my talk.
Great, thank you very much, Nikolai. So we don't have any questions. We have one from Mutu. So firstly, does the lower bound extend to deterministic functionalities? For example, by adding an input to each party to coin toss the index?
I'm actually not sure about the deterministic case. I think we need randomness, at least with the proof techniques used in this paper. But I'm not actually sure whether or not the lower bound extends to the deterministic setting.
I think it sort of depends, I guess, what you mean exactly by extending it. I do think that one could probably just transfer the randomness to random choice of the inputs, right? So if you would assume that like people would have, I guess that's what Mutu means, that if you have inputs from each party, that you would say XOR together to get this random index, that then I think that would have essentially the same effect as far as I can see right now.
Yep. Okay, and the second question from Mutu is, can we get around the lower bound if we assume one-way functions? In other words, does it hold in the random oracle model?
I would think not, but maybe even is able to elaborate on that.
I wouldn't dare to say much about this at this point. I would. I'm not sure. I do think that if you would, so it depends, right? I mean, if we assume one-way function, I think definitely not, because but then of course, if you assume one-way functions in a non-black box way, you would certainly, if you would exploit this, you would have to lose the perfect security, and then it's a totally different question. If you assume random oracles instead, who knows? I have no idea.
Okay, so interesting open question. And then a question from Nacho. Are there deterministic functionalities for which the same lower bound holds as for IP?
And I suppose that even answered this question if we instead like transfer the randomness to the inputs of the parties, then it should be the same.
Yeah, sure. Okay, so let's quickly try and get a couple more from Antigone. Does this hold in the preprocessing model?
So in the I'm actually not sure about this. Maybe you would be able to save some of the communication.
You probably would, because my first reaction is to say the answer is no, because what you can do with pre-processing is you can do this idea of pre-processing a random secret sharing, and if the party with the input that's relevant here already knows the random thing that you secret shared, you can just broadcast the difference between your actual value and the random value. And this would seem like something which is much simpler, at least, than having to establish a sharing of that input from scratch. So therefore, my intuitive guess would be no. There's no lower bound for the input phase in that case.
Wouldn't you already get something more efficient by using the protocol by Claudio and Yuval, where you have basically the whole function table secret shared in the preprocessing?
That's probably true too. But you still have to determine the inputs in some way, right?
Yeah, sure.